Okay, so today we're going to talk about the product rule. This is one of the first types of more complex derivatives we're going to be dealing with in our calculus units. The product rule allows us to take the derivative of two differentiable functions that are multiplying together. And that's what this right here, this symbol means, d dx. It means the derivative of a function with respect to x. You'll see this a lot, this simple expression, d dx. So if I'm doing f of x times g of x, what this means is the product will work out as the derivative of the first, f of x times g of x, plus f of x times the derivative of g of x. Since there's a plus sign, the order doesn't really matter. You could do g prime times f plus f prime times g, but just remember in this particular order, this pattern. Derivative of the first times the second, plus the first times the derivative of the second. You're going to have to take both derivatives, but you're not going to just multiply the two derivatives together. There has to be the original function times the derivative with the plus sign in between. The common mistake is just to do that. Do the derivative of the first function times the derivative of the second function. It's not correct. You've got to be careful with that. This is an example of two separate functions. We have f of x equals 3x squared times sine of x. This right here is really the first function. This is the second function. So we have a power rule right here and then a trig function. They don't combine together, so they cannot be considered one continuous function. So the derivative of this, again, derivative of the first part, so derivative of 3x squared, I bring the 2 in front, it's 6x, times our second function, sine of x. And then plus our original first function times the derivative of the second function. The derivative of sine is cosine. So there we go. The derivative of this function is 6x sine of x plus 3x squared cosine of x. The key is to, again, identify your two separate functions and separate them out accordingly. 3x squared sine of x, it's easy to see they were two separate ones. One's trig, one's a polynomial. Or a monomial, actually. Same thing here. We've got now a bunch of different product rules. We have 8x and cosine of x in this first part, and then a negative 2x squared and then sine x in the second part. So we're going to deal with the 8x cosine x part first. So the derivative of the first, or 8x, is just simply 8, and then times the second, cosine of x, plus our first function, 8x, times the derivative of the second function, which is a negative sine of x. So then we have plus the derivative of our first function. The first function is negative 2x squared. It becomes negative 4x sine of x. Plus, again, our first function, negative 2x squared, times the derivative of the second function, which is cosine of x. So we should distribute our negatives and make this into one neater looking problem. So we have 8 cosine of x minus 8x sine x minus 4x sine of x minus 2x squared cosine of x. Well, we notice we actually can combine like terms right here. They're both an x sine x problem. So we have 8 cosine of x. The negative 8 minus 4 is a negative 12, so negative 12x sine x minus 2x squared cosine of x. So again, that's how the product rule is working. You're taking derivatives of the first function times the second function plus the first function times the second function. There could be a whole string of product rules together. You just take them all one step at a time. The key is, for a product rule, there should always be two separate expressions with a plus sign or a minus sign if there's negatives going on left over. If you don't have two separate expressions, if you just did, for example, derivative of 8x is 8, derivative of cosine is negative sine, and said this, that would be incorrect. You can't combine them into one step. There must be a separation. Now, for a problem like this, there's two different ways of looking at it. You could consider this a product rule and do the derivative of the first part times the second plus the first times the derivative of the second. Or you could distribute and FOIL this expression in to make it a polynomial, because they're just simply all polynomial expressions. Both will give you the same final answer. Just to practice our product rule, we'll use the product rule for this particular problem. So, product rule says the derivative of the first, which is just simply 2x, times our second function, x squared plus 5x minus 2. and then plus our first function times derivative of the second. Derivative of x squared is 2x. Derivative of 5x is 5. And the 2 goes away. Now, unlike the previous problems, we don't want to leave it like this because these are all polynomial, these are all variables. We should distribute in FOIL and see, do I have anything in common? So I have 2x cubed plus 10x squared minus 4x. And when I FOIL, I get 2x cubed plus 5x squared minus 6x minus 15. So I can combine my like terms and get 4x cubed. So x cubed and 2x cubed combine. A positive 15x squared. A negative 10x. And then a negative 15. Which would be the final answer. So ultimately, it's up to you. I would probably personally, for this particular problem, would have just FOILed out the x squared minus 3 and the x squared plus 5x minus 2 into one long polynomial and taken its derivative from there. In my opinion, at least, I'm less likely to make a mistake in that step than I am later on. Ultimately, it doesn't matter. You will still have this final answer regardless, which method you use. The product rule wasn't that bad to use in this particular case, so it's not a bad idea to do that, as long as you, again, distribute and FOIL properly. Now, for this example, this is not a product rule problem. Because, yes, I do have a function, square root of x times x squared plus 2, so I have a first and second function. But unlike all the previous ones, this one is very straightforward. I should just distribute the square root of x into this expression. When I do that, I get x to the 5/2. Because remember, this is really x to the 1/2, so when I add 2 plus a half, I get 5x. Plus 2x to the 1/2 power. This is now a very straightforward polynomial that I do my usual power rule for the derivative. Exponent goes in front, decrease it by 1. Exponent goes in front, so 2 times a half cancels. Exponent decreases by 1. So you're going to want to be careful. Don't assume you have to use a product rule every single time it looks like you have a product. In cases like the previous two examples, you could distribute in FOIL or just very simply distribute. Again, in the previous example, it's either way. It's your call. Both ways will work. They probably give you the same amount of time and effort to solve the problem. So ultimately, it doesn't really matter. For this example, it is much quicker just to do a simple distribution of x to the 1/2 into it and then do a simple derivative. One step, you're done. Again, not all problems will do that. Typically, when you're dealing with a trig and the polynomial, they don't combine anyway, so you're required to use your product rule. Keep that kind of stuff in mind. Now, since we now know the product rule, we could technically have derived these functions right here: tangent, secant, cotangent, and cosecant. Their derivatives are secant squared, secant x, tangent x, negative cosecant squared, negative cosecant cotangent. And actually, these require the quotient rule to derive, so maybe we couldn't have done that. But still, we can still find these, and we're going to use these now. So like the derivative of sine is cosine, derivative of cosine is negative sine, these four simple trig derivatives are ones you need to make sure you know. You will see them coming up a lot. So if I want to find the derivative of 9 secant x, well, this is not a product rule because 9 is not a function, it's just simply a number. So I only worry about the actual function, secant x. Derivative of secant is secant x tangent x. So our derivative is 9 secant x tangent x. Pretty straightforward. Now for this one, this is a product rule because the first part, the 4x cubed, is an actual function. So, product rule says I do the derivative of the first. Derivative of 4x cubed, 3 comes in front, so it's 12x squared. And then times the second function, tangent x. And then plus our first function times the derivative of the second. And the derivative of tangent will always be secant squared. So it's 4x cubed secant squared of x. So again, this one right here, not a product rule because 9 is not a function, it's just simply a number. This one is because 4x cubed is a function. It's got a variable. Why don't you take a look at this one on your own. Very straightforward, same concept. We have our first function, 5x squared. Second function, cosecant x. Go ahead and apply your product rule to get your final answer. So I will pause the video while you work on that. Okay, so for this one, your final answer should be 10x cosecant x minus 5x squared cosecant x cotangent x. Again, product rule, derivative of 5x squared is 10x, so 10x times cosecant. And then for the second part, the 5x squared times derivative of cosecant is negative cosecant cotangent. That's how we got that answer. Okay, so that's your product rule. You're going to see this a lot. It is very useful. The key is making sure you remember to separate out properly. Derivative of the first times the second, plus the first times the derivative of the second. There should be two separate answers when you do your product rule properly. Notice there's a plus sign or a minus sign depending upon if there was negatives for your derivative. So that was our product rule. Next time we're going to talk about our quotient rule. What happens when we divide two functions and take the derivative. So I will see you next time.